As the world grapples with climate change and carbon dioxide becomes the noxious gas, there is much talk of finding a solution for evergreen energy. And one of the solutions which the world has talked about is fusion energy. And one of the places where fusion energy may first be tapped in the world, it's still far away, not so soon, is at the ITER project in France. And I have with me Laban Coblentz, who's a nuclear fission expert and a person who works with ITER in France. Laban, why should the world be excited about fusion energy?
Well, I think there are 4 reasons that set fusion really apart. First is that it is a massive, continuous, reliable source of clean energy. So what I mean by that is that you have a really millions of years of supply of fuel, unlike any other energy source other than renewable. And unlike the renewables, and in complementarity to the renewables, fusion is continuous, reliable. It is a baseload source of energy. Secondly, it is extremely safe. We have learned how to make nuclear fission a safe source of energy, but we know that nuclear fission causes anxiety in the public mind because of accidents like we've had and so forth at Chernobyl, Fukushima. The physics of fusion are very different and prevent any similar source of a meltdown or anything of that sort. So fusion is very safe. Third, fusion does not have the buildup of waste, so it does not have a long-lived, high-activity radioactive waste legacy to deal with. And fourth, we believe that fusion will be extremely economic. Not only fusion has, like fission, a large capital build followed by very low operating and maintenance costs, but what is particularly different is that because the fuel is available in seawater, and equally accessible to all countries, what that results in is no more competitive economics over access to petroleum or other limited resources. So fusion has sort of the holy grail characteristics of energy.
If it's so good, why haven't we done it today or yesterday, to be more precise?
It's a perfect question. It's because it's really difficult. We have been working on this. We knew about fusion in the stars. We knew that fusion was the source of most life and heat and everything else on Earth because this is how the sun makes its energy. We knew that since about the 1920s. But the sun does that with gravitational force. It compresses the hydrogen to such an extent that fusion occurs. To do that on Earth, we don't have an equivalent gravitation. So the question began immediately, how could we harness this? It was the late 1950s before the idea really came up of magnetic confinement in the shape of an apple or the shape of a donut, that this could possibly be a source. And immediately the technology, the experimentation began, and we have frankly conquered one problem after another, but we are only now getting to the point of building at industrial scale.
So how soon can we see ITER, and give the full form for my viewers for ITER, and how soon can we see it up and running?
Sure. So ITER is just entering. We are just having the largest components beginning to arrive on site this year. We will begin full-on assembly phase next year, 2020, and we will have an operational machine by 2025. The following 10 years, between 2025 and 2035, will be a series of experiments followed by more assembly, followed by experiments, more assembly. So full deuterium-tritium fusion in 2035. And with a few years of experimentation, at that we will be designing the commercial machines that follow.
By then, the global temperatures would be much higher. How can this process be accelerated? Because that is what the world really wants. Are you guys sitting back on your seats and not doing much about it?
It's a very good question. You know, we have had this discussion for a very long time. The truth is that the schedule that we're working toward in 2025 is what is called best technically achievable schedule. Some of these components individually are taking between 3 and 5 years to produce. So the vision with fusion undoubtedly is long-term. There are certain things that could accelerate the deployment. For one thing, advances in materials science, which are going quite rapidly, advances in fabrication, advanced manufacturing, which is going very, very quickly. And many people believe that the advances in artificial intelligence, the ability to analyze and move much more quickly on the analysis and conclusions from huge chunks of data, could accelerate the process. But I think that if you look at the members of the ITER project, which are China, Europe, the full European Union and Switzerland, India, Japan, Korea, Russia, and the United States, there are differences in terms of the urgency timescale with which they approach. Probably the most ambitious fusion roadmap nationally would be that of China, and China is already working on the machine that will follow ITER, and China hopes to begin building that machine really by between 2025 and 2030, once ITER has verified its general functionality. So you will hear China talk about connecting an ITER-like machine to the grid by perhaps 2040, but that's probably the most ambitious of them.
The one which drags you down is America?
I would not say drags us down. Certainly, if you look at the sense of urgency about energy, the U.S. has quite an abundant supply at this point of petroleum resources, and that takes away some of the urgency that perhaps China and India, for example, and even Korea and Japan have about really getting an alternative baseload source of energy much more quickly. I do think that in terms of contributing to the project, all of the members have been contributing with equal sense of urgency, scientific curiosity, engineering excellence. Each one of them is pushing the boundaries of their different disciplines as they supply components to ITER.
We do this interview sitting in Mumbai, India, which is the headquarters for the Department of Atomic Energy, which leads the ITER India project. What is India's contribution to ITER and how is it progressing?
So ITER was designed in a very strange way. For a machine that is this complicated, one might think that you would give it to a very large company like Tata or Larsen & Toubro or Siemens or one of these super companies. In fact, this was done differently because every member wanted to benefit as much as possible from the different technologies going into ITER. So this machine was subdivided. You really have more than 1 million components that are being assembled in factories all over the world. In the case of India, for the reactor, the tokamak machine, India is making the largest component, which is the giant vessel that houses everything, which is called the cryostat. It's so big that it cannot be actually made and shipped in entirety. It is made in pieces, shipped by ship to ITER. And there, a team of German welders under Indian supervision is complying with French nuclear safety regulation on an international site to assemble. So that's one. India is also supplying the in-wall shielding, about 8,000 tiny components, not tiny, they weigh quite a lot actually, but they are all going in between the two walls of the double-walled vacuum vessel. India is supplying the cryogenics lines that feed the plant that will supercool the magnets with liquid helium, as well as parts of the cooling water system that take off the heat generated by the ITER tokamak. They're doing quite a lot in diagnostics. supplying some electrical conversion components, supplying some power sources for the heating and cooling drive systems. So actually quite a lot.
So is it correct that the world's single largest refrigerator would be at Cadarache in France?
That's correct. I sometimes joke with my colleagues at CERN, who are our partners in some aspects of research, because if you took all of the different CERN accelerators and so forth, that you combined all of the cryogenic system, they would be slightly larger than ITER. But ours is certainly the single largest single platform refrigeration system, cryogenic system in the world.
And is it correct that the single largest refrigerator for the world is being built and made by Indian company and by India and being given to ITER?
Sure. There are two versions of refrigerator, if we call it that. There is what you have for the electromagnets. They are superconducting electromagnets. And so to be superconducting, they have to be cooled with liquid helium down to almost absolute zero, minus 269 degrees. For that, India is supplying a lot of the cryo lines, the cryogenics lines. But then in addition, perhaps confusingly, there is the cryostat. The cryostat is the giant vessel that will be at light vacuum in which the entire system is housed, and ITER is supplying also that, the cryostat.
Meaning ITER India?
ITER India, sorry, yes.
And what has been ITER Global's experience in interacting with ITER India?
Well, I think just that of an essential partner. I mean, I could say that, I suppose, about each one of the ITER member partners, that they're each essential. But I think what we find that is really unique about India, for one thing, some of the Larsen and Toubro supplying some of these giant forging facilities where really large components could be made to what might also almost be seen as insane technical specifications, very, very large, but needing to be shipped with no deformity, needing to fit together with no deformity. So certainly the Indian innovation has come with that. But also, I think just in general, India has this very, very strong base of nuclear fission expertise, coupled with large infrastructure project expertise, coupled with a very deep scientific base and a great deal of hunger for new energy systems. And all of those things have driven India to be an eager, a cooperative, a very willing partner in each of these system supplies that we've talked about.
Is there any way it can be accelerated, that we get the energy out of fusion faster than 2040? And also, this needs to be multiplied.
Yes, I don't think so. I would not say that it's impossible, and we certainly, if you talk to some of the private sector enterprises that are working on, say, less tested, higher risk models, they will tell you that they have goals that are somewhat more ambitious, and we certainly cheer them on in those goals. But what we know about, for example, the amount of time that it took for humans to deploy what seems commonplace now, petroleum resources, fossil fuel resources, that really occurred over more than a 100-year period, from really discovering and very occasional use of an oil in a certain way to complete refinement and use in the way that we use it today. The same is true for most new industries, new production. So I don't think that there is a way to deploy it faster, unless what I would say is that there are parts of what happens perhaps after 2025 that if globally we said this is our quote moonshot, this is our global ambition to make this happen. Certainly there are certain elements of the remaining science to be discovered, some of the things associated with efficient breeding of tritium, some of the things, the key with ITER that will not be faster is the burning plasma, but we might be able, with sufficient funding, with sufficient passion, which is really driven by political support, we might be able to accelerate part of that, certainly.
And ultimately, to me, it seemed it's a very complex machine from whatever presentations I have seen. Mm-hmm. Unlike the other mega science projects which the world is doing, mm-hmm. this damn thing needs to be cloned and multiplied.
Yes.
Because having a one-off ITER sitting at Cadarache, France, which is already flush with energy, is not going to solve the global energy problems.
Right.
How do you hope to multiply such a complex machine with 1 million parts?
Yeah, this is where I would say that the advances that we have seen in the past, really recently, even in the past 10 years, certainly in the past 30 years, but even in the past 10 years, what we have seen with advances in material science, in fabrication technology, and in supercomputers leading to artificial intelligence, that would suggest that the ability to learn from all of the physics data that has been collected, all of the plasma performance, et cetera, the ability to generate the optimum, to optimize the materials that are used to withstand this very, very high heat flux, and the ability to then replicate what is the most sensible direction for new design, and to fabricate in ways that make today's fabrication methods look positively antique. Those are things, I think, that will lead to more rapid deployment.
Occasionally one hears that helium-3 could be used in fusion energy. Is there any merit in that argument?
To my knowledge, no. I think that there are certainly experiments. We talk about, there's also look at other materials in terms of the fusion events that come from them. And certainly you get in each case, you get a powerful rendition of the same Einsteinian E equals mc squared, a little bit of matter converted to a lot of energy. But in terms of what we have seen from the reliability of the research, the one that we really think is, and this is quite generally felt globally, the one reaction that we feel is best to use is still hydrogen. It's still deuterium and tritium, two isotopes of hydrogen, for the most easily harnessed, combined with the best power output.
And we have lots of that.
We have lots of that.
So ITER promising evergreen energy when it goes up and running?
Yes, absolutely.
And again, I press on you, how can we get it faster? I think India needs a solution, and the world needs a solution like this far quicker than 2040, 2050. I think, and again I say, something needs to be done to accelerate this process.
I think that actually journalists putting out that message to governments around the world is one of the most effective forces for acceleration that we can hope for.
So that was Laban Coblentz from the ITER project in Cadarache, France, telling us that ITER is progressing well. It has had a fits and starts of progress. They always say, fusion energy, 20 years from now. Every time you ask, it's 20 years from now. But then there is hope that by very soon we'll have the ITER project up and running, and by 2040 it may generate electricity which is connected to the grid, and soon have multiplication of those reactors, which hopefully would be safer than the fission reactors we use today, and offer a base load solution for energy. That is what the world needs. In Mumbai, Pallava, Bagla.